Hey everyone, welcome back to TechBit Academy. Please like this video and subscribe to the channel.
Welcome to this explainer. Today we're unpacking the hidden, fundamental architecture that powers the modern digital marvels we rely on every single day. We're talking about the heavy lifters, from the systems training massive AI models to the ones running complex global weather forecasts. Let's dive right into the building blocks of parallel computing. Okay, let's kick things off with the big question. How exactly do computers tackle problems that are just insanely massive? When the math gets too heavy or a data set gets too wide, a single processing chip eventually hits a hard physical wall. The answer? Divide and conquer. And to really understand how that magic happens, we need to look at the terminology and the architecture that makes it all possible. Here is our structural roadmap for today. We're looking at 1. The brain, CPUs and cores. 2. The work, tasks and pipelining. 3. The machine, nodes and supercomputers. And finally, 4. The ecosystem, memory and communications. All right, section 1, the brain, CPUs and cores. Think of a core as an independent worker right inside a modern CPU. Instead of having just one brain doing everything sequentially, each core is its own distinct execution unit. It follows its own stream of instructions and works entirely in parallel with its neighbors. It's a real game changer for speed. Now, physically, these cores group together into what we call sockets, and each socket features its own distinct memory. But the absolute genius of this hardware design is how collaborative it is. In a multi-socket CPU, the underlying infrastructure actively allows memory sharing across those different sockets. So you get localized organization, but collaborative memory sharing under the hood. Moving right along to section 2, the work, tasks and pipelining. So to actually parallelize work, we first have to define what a task is. It's really just a logically discrete section of computational work, like a program, for instance. By definition, a parallel program is just multiple tasks executing simultaneously across multiple processors. To really wrap our heads around how processors handle these tasks so efficiently, think about an industrial assembly line. You wouldn't have one single engineer build a car from scratch, right? You pass it down the line. Well, parallel computing operates on that exact same logic. And that brings us to pipelining. It's a 3-step dance. First, you break a task down into discrete steps. Second, you assign those steps to different processor units. And third, you keep the inputs streaming continuously through the system. It drastically accelerates the throughput because, and this is absolutely crucial, it ensures no processor is ever just sitting around idle. Next up, section 3, the machine, nodes and supercomputers. Let's zoom out a bit. Now we're looking at the node. Picture a node as a standalone powerhouse, literally a computer in a box. It comes fully loaded with multiple processors and cores, its own local memory, and the vital network interfaces it desperately needs to communicate with the outside world. And here is where we achieve that incredible macro-scale power. A supercomputer isn't just one giant monolithic chip. No way. It's actually constructed by networking hundreds or even thousands of these individual nodes together. The true scale of processing power is born from that connection, not just the isolated hardware itself. Finally, section 4, the ecosystem, memory and communications. So all these networked nodes absolutely need a systemic way to store data, right? On the hardware side, we basically have 2 paradigms. There's shared memory, where all processors access one common physical memory pool, and then there's distributed memory, which relies on a network to access dispersed physical memory that isn't shared. A prime example of this shared memory concept is the Symmetric Multi-Processor, or SMP design. In this kind of setup, multiple processors share one single address space. But what's really important here is that it creates a perfectly leveled playing field. Every single processor has strictly equal access to memory, disk space, and all other resources. But if we shift our perspective over to the software side of things, it gets interesting. Tasks written for a shared memory model all map to the exact same picture of logical memory. Conversely, tasks programmed for distributed memory only logically see their local machine's memory. They are effectively completely blind to the memory of neighboring nodes running parallel tasks. Because distributed tasks are essentially blind to one another, they rely entirely on active communications to bridge the gap. Whether they're exchanging data over a shared memory bus in an SMP setup or firing packets across a sprawling network, this communication is the glue. It's what actually allows a massive problem to be solved collaboratively. As we wrap up this explainer on how modern machines scale, I want to leave you with something to chew on. We can add more cores, build massive nodes, and pipeline millions of tasks. But as we push the absolute boundaries of scale, will our communication networks, the very pathways required for these independent tasks to share data, ultimately become the final inescapable bottleneck to computing speed? Thanks for joining me.